Next, we have Dr. Sachin Garg, who is a seasoned technology developer with over 25 years of experience in both academia and industry. He has been a pioneer in the open source movement in India, and currently he is the CTO of Navankur IT. In this talk, he will dive into the recent discovery of a critical vulnerability. He will also discuss its implications on the FOSS community and the importance of maintaining trust in the software supply chain. So please welcome Dr. Sachin Garg.
Hi everyone. Good evening to everyone, all of you. And I hope you're enjoying the day here. It's late. I think we have run a bit out of time. So my talk is about the XZ Utils vulnerability, which was discovered in March, April of this year. It was a critical vulnerability that is scored 10 on the common vulnerability scoring thing. And why I'm discussing this is because that vulnerability actually had significant issues impact on the entire FOSS community. So I'll just talk a bit about myself, what the vulnerability is, that's the structure, what are the techniques used, and what have been the key learnings and what could be a call to action here. I have been one of the earliest, though it's immodest to say that, but one of the earliest users of FOSS Linux in India. Started with it around 1995 with kernel version 1 or dot something. I moved to Bangalore. I was a regular at the contributor to the BLUG, which is the Bangalore Linux Users Group at that time. I also gave a talk last year about 25 years of BLUG, a retrospective which discussed how the community was formed here and what happened. I was also instrumental in ensuring that Wipro was sponsored FOSS in 2006. Wipro at that time was very notorious for not doing much FOSS events. But now they are big into FOSS and legal issues. I've been interested in almost all aspects of FOSS, the socio-political one, the economics ones, community building, IP stuff. And this is what led me to pursue a PhD in technology and public policy, where I actually looked at big data and its impact on society. And that's if anybody wants to connect with me, they can scan the QR code to connect with me on LinkedIn. So what is the XZ vulnerability? XZ I said because that's the way we have been taught in school about Z and not Z. So that's the point. So this is the few of the news items that came around in March or rather April of this year, talking about Red Hat warns of urgent vulnerability impacting major distros. Ubuntu 24.04 was also delayed a bit because of this. And there were very serious issues about this vulnerability because this was injected by a malicious actor, which we'll get to, and it was a complicated one to understand. So that is what why this becomes important for us to talk to and understand what it was and possibly what the community can do to ensure that these things, well, they will happen, continue to happen, but at least we have some sort of plans to fix them before they get out of hand. So what is XZ Utils? If you understand, there's a file extension called .xz. So XZ is a compression utility which implements it's a lossless compression, which is, if you know, compression can be either lossless or lossy. Lossy compression is of the type that we get with JPEG files, MP3s, while lossless compression is most of the compression that we would use. Even PNG is a lossless compression. There is no data loss. But lossy compression, there is an amount of data loss. But whenever we are sending data, we don't want our data to be lost, so we want lossless compression to happen. The Lempel-Ziv Markov chain algorithm, that is the LZMA algorithm, it's a C implementation of that, C99 implementation. And the reason XZ is important is because it has higher compression rates than alternatives. For example, we note here that gzip and bzip2, what is the size differences? It's a 38% smaller file for 1.6 GB. And decompression speeds are between bzip2 and gzip. So it's almost, gz is almost 23.4% slower, which means that for stuff like the Linux kernel that is compressed once and decompressed multiple times, it makes a lot of sense to save bandwidth, disk space by downloading XZ files, Well, compression speeds are actually slower. It's much, much slower than gzip. It's slightly slower than bzip2. bzip2 But the point is that you don't compress data very often. You compress data once, but the same file gets downloaded multiple times, so you essentially save a lot in aggregate bandwidth and aggregate disk space by using something like XZ. The latest version is 5.6.2, released on 29th May of this year. And this backdoor was found in versions 5.6.0 and 5.6.1. So what is, as I discovered, this vulnerability was given the name of 2024-3094. It is score 10 on the common vulnerability scoring system, which is the highest. That means it was an extremely critical vulnerability. It was discovered in late March of 2024 by Andreas Freund, who is a Postgres developer working at Microsoft. Hello. He posted this on the on, I think, the Postgres mailing list, or one of those mailing lists, where it is, and this is a tweet that he put in, that I'm doing some micro benchmarking, needed to quiet the system to reduce noise, so I saw SSHD processes were using a surprising amount of CPU, despite immediately failing because of wrong usernames, etc. Profiled SSHD showed lots of CPU time in liblzma, with perf unable to attribute it to a symbol, got suspicious, recalled that I had seen an odd Valgrind complaint in automated testing of Postgres a few weeks earlier after package updates, and really required. So essentially, the interesting thing here is that he discovered this because SSH logins were failing or were almost 3 times slower. That is 0.8 seconds versus the 0.3 seconds that he was seeing earlier. So it is this sort of a, let us say, understanding of the system, realization of what is expected, that he was able to track this down. And similarly, just a segue, there's a wonderful book on hacker, how to find a hacker, called The Cuckoo's Egg, by this guy called Clifford Stoll, written in the early 80s. He's an astronomer working at Lawrence Berkeley Laboratory, and he finds that there's an accounting error, I think, of some 75 cents. And his boss asked him to track it down, and when he tracks it down, he found that there's a hacker in Germany who has been hacking into the systems and actually getting into top secret CIA meter systems. So that's just a point to make that how much a little difference, if you are careful with your system and understand it, it can actually help uncover bugs. Now, exit vulnerability is a sophisticated exploit. It's an extremely sophisticated exploit. A lot of it has been written about it. And here I'm only going to talk on the tip of the iceberg. It's a pretty complicated technological thing, and I don't understand a lot of the details. Excuse me for that. So I'll basically try to give a gist here. It relies on various linker, loader, and compiler features. That is low-level stuff. The code is obfuscated. Data is compressed. There are complex binary data structures in place. And there are complicated shell scripts. And the challenge is that it used social engineering to get commit privileges to a malicious actor, who in turn was able to inject this malicious code. And the exploitation done using systemd notifications when SSHD. So the idea is that when your SSH server is up, it notifies systemd that I am up, so that it can tell everybody that it has that it is finished starting up. And that was the key thing that it was using to trap into OpenSSH. So what are techniques used? The techniques is that the exploit is hidden in various techniques in code, as I said, while building and while loading. It only targets the specific architectures and OpenSSH. So that is so it was not targeting everything. It is not targeting the ARM platform, or it was not targeting any other program other than OpenSSH, which is also a reason why it possibly was not discovered much earlier. And the code, in the code, it hides the strings using specific data structures, complex data structures, which means that one cannot use the strings command to figure out what is happening. So if it says OpenSSH symbols and things like that, you cannot just do a strings and be able to figure out what it is. There's a build time. It injects code which is hidden in test files, supposedly compressed test files meant to be failed test artifacts, but there are ways to do it, and that is where the code comes in. And while loading, it uses features that are specific to the GNU C compiler and the linker. So hiding strings in code. To hide strings in code, it doesn't embed the strings per se, as I said, and hence you cannot use the strings command. What it does is it uses a data structure called a tree or data structure or Radix tree. Basically, the idea is that a tree is formed of each character in the string, and that tree is then traversed to create the entire string. And this is an extremely simplified image of the data structure. Okay, we can't see it. So, but in actual, the data structure is a binary data structure, so it doesn't really store any of the ASCII characters or anything to be able to figure it. It stores binary data, which is extremely difficult to get a hand to. Then, as I said, there's obfuscated code at build time. It targets only the x86, 64 Linux, GCC, and GNU compiler. During the build process, certain hidden directories are created and used. Hence, if you're not careful, you do not know what the build program is, what the build path is. It is very easy to overlook that. And if the build fails, or those directories will get deleted. So during the build, so there are tools that it has used, techniques that have been used to ensure that very little trace is left of what has really happened. And how many of you have actually done a makefile compilations or the Linux kernel first time? How many times have you looked at the makefile output and seen the log files? Not much, right? Nobody really cares about a lot of that stuff. So if there are, and we don't really know the build process very well, so we don't really know what directories are supposed to traverse, where it's supposed to go, and things like that. So if you are, unless you are a guy who is actually doing the code, you have written it yourself. Even if you've written it yourself, you don't give too much of a thought as to how it happens. A lot of the configure, automake, all those tools take care of it. And that is one of the fallacies that have been exploited. So what it does is modifies this makefile, and it injects an obfuscated script. As I said, these scripts are uploaded as test files. What this person had done is he had uploaded a set of test files which are supposed to be corrupt, XZ files, so possibly test cases of testing for corruptions. But actually these files weren't really corrupted. They were actual compressed, XZ compressed files. However, certain header or magic strings were reversed or altered so that your file command may not know that it was XZ. A test case would have said that it is corrupted, but this script that this person had installed would actually do some changes in that file and ensure that it replaces it, and then it can do a uncompression and do it. So this is, for example, is what sort of obfuscated code is. So if how many people can really understand what this shell script actually does? It's extremely difficult to be able to read this, run this through manually, or figure it out that what each line is doing. You are exporting a particular variable. You are taking what is head minus C 1024 do, and then you do a file, all these random, you're translating different files. You are taking lots of, so the point is that this was, so the obfuscated code is this. You don't even know what it is doing. But unobfuscated, so there's a snippet of the unobfuscated code that is there. Here. So this is what it does. This may not be the exact same snippet, but it puts some flags there that see the P is equal to minus, that's the compiler flags, it evaluates certain variables. So that is what, but all of this is hidden inside this obfuscated code. And this obfuscated code is injected at the end of, is executed at the end of configure, and hence you get this sort of thing. This file also contains additional binary data that is the part of the actual backdoor, which is a 64-bit relocatable ELF library, and that is linked into the final liblzma. So this file contains a script that injects itself. It also has a small binary file which is actually injected into the actual library. So this file is hidden inside a test file that no one really knows really exists or what it does. To the casual user, it is just one of those files as an artifact for testing, which is a failure test. So what happens during the linking and loading time? So this is how it was done during the code compile time and how it was done. The liblzma library ends up being loaded into OpenSSH on some distributions because how it gets into OpenSSH is because as systemd links into liblzma for general file compression and decompression. So that is the usage. And that is why and systemd notifications are being used by OpenSSH. And okay. So one of the tools it uses is called an indirect function or an ifunc mechanism, which is actually a function of GNU-C library that allows people to specify their versions of functions and select which version to use at the dynamic linking time. The Backdoor provides its own versions of the indirect function resolver called these CRC32 resolve and 64 resolve that select versions of that is CRC cyclic redundancy checks. And it does, liblzma does not usually use indirect functions, but using faster functions to do this sort of thing seems to be a plausible use case, and possibly that is why the file was actually named as liblzma laccr64 fast.o. So that was the name of the file that was there, the exploit, which was in turn hidden inside a test file. So another thing that it was used is called audit hooks. So the dynamic linker provides something called audit hooks. Now this is top level stuff. There's a lot of literature here. I've got a lot of references at the end of the session. Somebody can go in and look at technically what it really does. So because liblzma is loaded fairly early in the link order of OpenSSH, so the OpenSSH cryptography functions, which are the ultimate target to be able to break through the certificate or break through the keys mechanism, have not been loaded yet. So to do this, something called the audit hook is used. And what happens is, whenever a symbol has to be resolved, the dynamic linker calls all the registered audit hooks. And the backdoor uses this to wait until this particular RSA public decrypt function is called, which is actually an it's a decryption function used to decrypt part of the RSS certificate when a connection is made. And the actual function is replaced by the backdoor's own version. Backdoor's own version is supposed to, when I read it, the article that I read was on lwn.net. And that was, I think, sometime in April. I'm not sure, April or in May. And that time they said they didn't had the time to go through the entire, people had not yet figured out what the backdoor exploit was trying to do. But the idea is that it was trying to extract keys or try to replace certificates with their own or try to connect to some other machines and things like that. So one doesn't know. And the challenge has been that because of the exploit, the code that was there and one could understand what was happening had been taken off by GitHub. GitHub had taken it away. And also because there is let us say, a theory that the entire exploit had not yet been put out there. And because of the complexity of the exploit and all the other things, there's also another doubt that it was actually state actors like China or Russia, most probably China, who were actually behind this whole thing. And this was being done incrementally in pieces, and the entire exploit had actually not been made public to who were targeting and what sort of things. So this is a fairly high-level description of what it is. A lot of it is pretty complicated. It requires deep linker, debugger knowledge, assembly language knowledge. And possibly that is also why the reason is that it wasn't targeting the ARM, which has a completely different architecture. The linker loader platforms are different. The way linking happens, the way runtime happens is different. So they just decided to target the most common architecture, that is x86 64. So this is what I've just put out. The few learnings that build systems are complex. As we all know, build systems have become extremely complex. We need to support multiple platforms. AutoConf, AutoMake are not very well understood. And because AutoConf and AutoMake are not very well understood, even upstream was actually configuring stuff and shipping tarballs. And that is where this was actually found. In the core code, the thing wasn't there, the exploit wasn't there, but it was in the tarball that was shipped. So somehow that's how it came to be. As we said, configure injects it at the end of the thing. So that's when you do a configure, and then you had a tarball, and that's where it was being shipped. It has a large attack surface. As I said, OpenSSH links with systemd, which links with liblzma for notifications. However, after this exploit had come out, I think Leonard Pottering, who wrote systemd, actually pointed out that it's not necessary to do this. If you just want notifications, there's possibly a simpler mechanism to do it. But the point is that that is what people were doing. Then social engineering. Jin Tan, who was the person who has been identified as the one who got the exploit in there, had gotten commit privileges after many years of work. There were lots of online profiles that were praising his work, etc. But another challenge is that not many people really know who the persona really was, or who are the people who were praising his work were. So it is like there was this virtual world versus the physical world. I do not know who I am. I don't have a reputation in the real world, but I have a great reputation. Like Satoshi guy who's done the Bitcoin thing, nobody knows who he is. So those are the sort of challenges that you have. And then there was this talk about software bill of materials, which is a very common thing. I think there was a talk just now going around in the auditorium. Software bill of materials are great, but they're not a solution for this type of problem. They are great to understand when a vulnerability has been found, what versions it is there, what versions it has been addressed, how to fix it, and to be able to know where it is coming from. But to be able to identify challenges that are happening in the code level, malicious code being injected, all SBOMs cannot help us. These things require continuous code audit reviews and stuff like that, the good old ways when you need to do it. And for another example of SBOM is I went to a Docker event, they talked about something called Docker if code, which seems interesting. I didn't, where it can actually tell you that these are the various CVEs that are there in a particular Docker container, and then you can fix it. So those tools are great for deployment purposes. But when you are really building systems or maintaining them, then we have to go beyond. And this is what I call as the call to action, the inevitable XKCD cartoon, which basically says that all modern digital infrastructure, the linchpin is somebody who has been maintaining stuff for ages, and thanklessly doing it, not really being, for example, the OpenSSL. If you remember, a few years ago, there was an OpenSSL vulnerability that was found because there weren't enough maintainers. Just today, there was a message on LWN, Linux Weekly Network, weekly news, that the maintainer of the Linux man pages is stepping down because he says that I have been working thanklessly for ages without being paid an iota of doing work. And that is some of the things that I think we as developers should possibly be stepping up to. The pain areas, the plumbing areas, the painful areas. It's great to do LLMs, it's great to do AI stuff, it's great to do all the sort of the flashy stuff. But in effect, actually what we really need to is now that we need to also become system engineers. We need to understand how the builds happen, how compilers work, how linkers work, how loaders work, how security is there, what are the challenges of security. We need to basically also be able to move down to a lower level and be able to, that's what I should say, that we need to do that. And so thanks, and any questions? So I'm holding a BOF session tomorrow at FOSS and Security at 3 p.m. in Audi 2. The idea is that this is I personally am not a security guy. Let me be very frank on that. I have zilch idea about really what security is essentially about. But because this vulnerability came in and it came into the FOSS thing, it becomes important. I thought that we should be talking about security and how we can build security in our systems, or how we can learn more about security. So, and I've also got to know from the FOSS United guys that They may be willing to sponsor some sort of projects that may work at the very basics. The fundamental issues, if one is willing to tackle, they might be willing to look at some sort of sponsorships. This was just in the air. I mean, he just said that you can call it out there that we may be able to do something. So, and that's where you can connect with me on LinkedIn. And as you can see, this presentation has been completely prepared using FOSS. No PowerPoint here. Fine. Thank you.